So what are electromaterials? These are materials that conduct electricity and can be found in the batteries that power our cameras and many modern appliances. The battery provides energy through the ability to move electrons from one electrode to the other, an ability strongly dependent on the size of the materials employed. We can move from the macro, the millimeter domain, down to the micro, where we encounter sizes similar to nerve cells, through to the nano, 1,000 times less than the diameter of a human hair, and here some fascinating things occur. So electron transfer to or movement through larger structures is often limited. However, as we move to the nano domain, we increase this rate of transfer and we increase the rate of transport of electrons through materials. So in the nano domain, surface features can influence even biological interactions, determining whether or not living cells, such as nerve cells or even muscle cells, will interact with that surface. We can now create nanostructures and nanostructured surfaces in a number of ways, in the form of long lengths of microfibers with nanostructured indentations. We could also use templates to grow ordered nanostructures, or even chemical vapor deposition methods to grow ordered nanotubes. We have found that certain nanostructured electromaterials, those based on organic conducting polymers, have amazing dynamic properties. We can provide an affinity for certain liquids or make the surface repel those same liquids using simple electrical stimulation. This same electrical stimulation can be tuned to cause localized release of biomolecules at an interface, promoting nerve growth, for example, or it can be used to encourage different polymer compositions through electrical stimulation to induce movement. Movement assisted by small electrical stimulation. We can therefore tune a surface to reject or accept cellular interactions, providing an exciting new platform for biomedical bionic devices. For example, the cochlear implant, invented by Professor Graham Clark, relies on electrodes to transmit stimuli from an external microphone through to the living nerve cells. The sound is transformed into electrical impulses, delivered to nerve cells and on to the brain. As we decrease the size of the electrodes, we can provide more sites of electrical stimulation and more effective bionic hearing. Damage to the spinal cord has devastating consequences. The development of an electrical conduit that will assist in spinal cord repair is another target of our research. The conduit must be compatible with the biological environment at the site of damage. We are fabricating microfiber structures that will be implanted at this site to achieve our mission. The nanostructure on the surface of these fibers influences the initial cellular interactions, while the microstructure plays a critical role in determining the direction of neuron outgrowth. We will use electrical stimulation to assist the nerve regeneration process. It is a great challenge, but the consequence of success means that we should never give up. A number of diseases, and of course trauma, can lead to muscle loss and the need for muscle regeneration. We're making electromaterials that provide an environment for muscle cell growth, directing their assembly into muscle fibers and finally tissue. We envisage that this regrown tissue can be transplanted into an environment where muscle regeneration is needed. All of these bionic devices need power to function. Conventional battery technology may not be the most appropriate. Our research into new biological sources of power is therefore critical. We are creating new biologically driven structures that can power the next generation of bionic implants. We are driven by the need to realize real clinical benefits from our exploratory and fundamental research programs.